Hello everyone, welcome back to the course again on architectural design of ICs. So, in the last class we have seen that this sign multiplication method. Okay. So, how we have extended the sign using that Boolean algebra. We have converted that, we know that said that z bar equals to 1 minus z and then z equals to 1 minus z bar. So, based on that two particular equation, so now we have come down to that how we can represent this as we are considering this sign multiplication. So, at that time because of the MSB of that both the multiplier and multiplicand they are with of negative weight. So, based on that we will get the partial product MSB that will also be in the negative. So, that will represent negative numbers. Okay. So, whenever we will add all these partial product, so at that time what I have to do? I have to extend the sign. So, how I can extend the sign? So, based on these two Boolean algebra, so how we have, that means come down to the equation something like this. Suppose for minus a4 x 0 bar, okay. So, that we have come down to the equation that is equals to, so minus a4 and then a4 x 0 bar and that is added with a4. Okay. So, that equation we have seen and we have continued to that with that particular concept or with that that means idea, and then we have come down to the architecture which are using lesser number of multiples whenever we are doing this sign multiplication method, which is known as this Bernoulli multiplier. But still we that means we have seen actually, or we have analyzed or we have observed that because of that particular notation what we are doing, we are increasing the maximum depth in corresponds to the unsigned multiplication. Okay. So, as we are increasing the depth, that means depth of addition operation in chain. So, as I am increasing the depth, that means I am increasing the delay too, because the number of stages for addition operation that will increase. So, that obviously it will increase the delay. So, how can I reduce that then? Or can I reduce that? So, that we will see today's class. So, in the last, that means in whenever we are seeing or we are reviewing the, that means sign addition operation. So, at that time we have seen this equation that x I equals to, x I can be represented as x I bar plus 1 minus 2, where x I dash equals to, that means that is the x I bar or not of x I. So, this equation can be same as this x I. Okay. So, this is the equation which we follows in 2's complement multiplier. So, if we follow this particular example or if we follow this that means this equation on that whatever for Bernoulli, that means Bernoulli multiplier we are getting. So, at the time for the this particular position, what the value we are getting, that is minus a4 x 0, here minus a4 x 1, this is minus a4 x 2, this is minus a4 x 3. So, now as I said that, so this is now this particular position. So, this is, if I consider this is a4 x 0, if this is a4 x 0, so then this particular equation can be written as a4 x 0 bar 1 over here minus 1 over here. That means, this equation is nothing but, if I consider this as a x I, so x I equals to x I bar plus 1 minus 2. So, minus 2 means it comes to the that minus 1 to the next MSB, and 1 means it is at the same position, along with x I is a4 x 0. So, it will be a4 x 0 bar. Okay. So, that means now instead of that, initially what we are doing? We are doing this as a4 x0 bar plus a4 minus 2 of a4. This equation has been represented in this manner, but now this equation has been represented using this, that is a4 x0 bar plus 1 minus 2. Okay. So, if we do for this all these values, if we do the same, so at that time what I will get at this particular position. So, this will be a4 x0 bar 1 over here. So, 1 1 will cancel over here, 1 1 here, 1 1 here and minus 1 at this particular position. So, what will be left at this particular position? This is a4 x1, this is a4 x2 bar, this is a4 x3 bar. Okay. And then for the next, this a3 x4, a2 x4, a1 x4 and a0 x4, on the same fashion again I can write this a0 x4 as a0 x4 bar plus 1 minus 2. This a1 x4 minus of a1 x4, that can be represented as a1 x4 bar, a1 x4 bar plus 1 minus 2. Okay. So, in this manner, if I just represented all these negative terms, so what I will get? I will get, so again 1 over here, minus 1 cancel, minus 1 plus 1 cancel, sorry, minus 1 plus 1 cancel, minus 1 plus 1 cancel. So, minus 1 at this particular position. So, a3 a4 a3 x4 bar, a2 x4 bar, whatever values I left, so that will come to this particular position. So, then finally what I have to do? Finally I have to add all this. Okay. So, now what is happening? So, this position was a4 x0 bar 1, a4 x1 1, so this one, and at this particular position there was minus 1 minus 1. Now, I have to combine this 1 and 1 means plus 1, plus 2. Okay. So, plus 2 means that one will be shifted to the next corresponding MSB. So, now this one that will come to, because of this 1 plus 1, that will come to this particular position with 1. Okay. So, then 1 minus 1 and minus 1, that is minus 2. So, then again this minus 1 will come to the 2 to the power 9 position. So, that means 2 to the power 9 is the minus 1 with 1, and instead initially I was getting 1 at 2 to the power 4 position, but now it comes to this 5th position, because 1 and 1 I am doing. So, that means 1 will come over here. So, what will be the final result? That means final circuit. Then I can represent it that this at this particular position there is no extra term. Initially what for that means that Bernoulli multiplier, what was there? There was a4 and x4 at this particular position, but in the modified Bernoulli multiplier it is not there. Okay. And then at this particular position, now this the 2 1 there, because of that this 1 is coming at this particular position, this 2 to the power 5 position. Okay. And here initially what was there? That means sorry, for I think for this particular position it was a4 bar and x4 bar, but it is also not required. So, 1 is coming over here at 2 to the power minus 2 to the power 9 position. Okay. So, that means now what is my maximum depth? That is 1, 2, 3, 4, 5 over here, 1, 2, 3, 4, 5 over here. So, that means now the depth is maximum 5. Okay. So, that means I can do this sign multiplication For unsigned multiplication, the maximum depth will be also of 5. For signed multiplication, this for this modified Bogli multiplier, the depth will be maximum depth will be of 5. Okay. So, that means now delay wise this circuit is improvised. Okay. So, this is the modified Bogli multiplier. Now, you can do anything, that means now you can use any of the tree, that means structure for addition of this each of the that means operands or each of these multiples, or you can use, that means for each of the stage you can use carry propagator adder or any, that means fast adder to add, that means to sum up all these partial products, that also you can do. Okay. So, now you can, that means do, or you can for the final products, to get the final products or to obtain the final products, now you can add these partial products in your way. You can do this tree method to add these partial products, or you can use any fast adders to sum up these partial products, or you can follow the serial manner also to do that. Okay. Now, it is your choice, but the corresponding multiples generation, that is basically done in this manner in modified Bogli multiplier. Okay. So, then there is, so that means this is the basic fundamentals of sign multiplication, which are basically this Bogli multiplier, and then we have seen this modified Bogli multiplier. Okay. Then there is another type of multiplication or multiplier architecture, which are known as this array multiplication. So, the name by itself, it says that means array means there will be kind of, it will be kind of 2D architecture. Okay. So, 2-dimensional architecture, that means one in vertical, one in horizontal. Okay. So, how I can do, or how I can compute this particular multiplication method, or I can implement one multiplier using this array architecture, that we will see now. So, in array multiplier, it is basically this carry save adder based partial product reduction tree. As we have seen that this if we follow this Wallace tree or this Dada tree method, their structure is very much irregular. Okay. So, that is why we get some the issues in VLSI implementation. What are the issues? Issues are come with this that means wearing of each of the cells and then placement of those cells. So, that becomes that means a major issue whenever we consider one huge number of, that means the word length for the inputs are more, at that time it becomes a serious issue for the VLSI implementation. For the lower number of bit width, it is not that much that means problematic, but if we consider 32 bit or 64 bit multiplication, so at that time it becomes a problematic or the complexity is increased for that Wallace tree or Dada tree method. Okay. So, then what is the, that means this array multiplication is, that means the alternative tree reduction method to do that. Okay. So, what is that? That means the problem of this irregularity in tree reduction, that or the tree multiplication, that can be solved if we use this array based multiplication method. But it is basically slower in terms of number of logic levels, and it gives me, as because the structure is very much that means regular, the flow of the data, that is very much easy, or that is very much regular, so that whenever we will follow this VLSI implementation or whenever we do this VLSI implementation, so at that time the problems or the complexity becomes lesser in compared to the tree based multiplication method. But the what is the problem here? The problem here is that it is slow in operation in compared to this tree reduction method. tree reduction method, whenever we have compared at that time, what we have seen, that tree reduction, that means tree based multiplier, they are very much faster in nature. Okay. So, used this tree reduction, that means tree based multiplier, whenever we need speed as a major concern. Okay. So, then this is the, that means basic 5 cross 5 unsigned array multiplier. So, in array multiplier what is there, that means the corresponding terms are basically coming through the carry save adder, then sum, then it produce sum and carry. So, then each of the levels it consider, because 2 of the inputs are basically coming to the next carry save level adder 2. So, then 0 1 a, sorry. So, this is for 0 1 a, 1, that means x 1 a, x 2 a, x 3 a, x 4 a. So, all are basically, that means added using this carry save adder, and finally, the bits has been added in carry ripple adder to get the corresponding results. So, here the as you see the corresponding critical path, at it passes through several, that means phase, that means the structure is what, one by one addition operation we are doing, we are not doing that in parallel. So, that is why the critical path is more. So, for m bit multiplier and n bit multiplicand, the critical passes through approximately m minus 1 plus m minus 1 full adder cell. Okay. So, that means for m bit and m bit multiplicand and multiplier both are of m bit. So, at that time it has to pass 2m minus 2 number of full adder cell. Okay. But it can be a good solution for computing Ax plus y. Okay. So, how to do that? That we will see in the, that means later of this, that means later of this slide. Okay. So, as we have discussed that, but the structure is very much regular. Okay. So, that means one by one you just put this corresponding input and then you will get the final results. Okay. So, this is the basic, or this is the, that means the idea of this array multiplication, and from this, looking to this picture, I can easily say that okay, the critical path is more, but the structure is very much regular. So, if we just follow this particular that array multiplier architecture, so at that time what is happening? So, that means each of this particular cell belongs to the, if I say this is the processing element, if I name this as processing elements. So, this is processing element 1, this is processing element 2, then 3, then 4, something like this. Okay. So, at this particular, from this particular positions, I am getting the corresponding outputs or the results. Okay. So, at the very beginning, where from we are starting, basically we are starting from this particular end. Okay. So, what we know, this is unsigned multiplication. So, what we know, that P0 is A0 x0, correct. So, A0 x0 is directly coming to this P0. Then what is my P1? What is my P1? That is A1 x0 plus A0 x1, correct. So, in this next you see what I am, this is P4. So, in P4 it consumes 3 input and produce 2 output. Okay. So, that means in this case, so A1 x0 and A0 x1, they are coming and they are producing this P1. Okay. So, then in P2, what is the case? in case of P2, it will be what it will be? It will be of A2x0 plus A1x1 plus A1x2, okay. And apart from that, what will be another thing which I have to add? That is the carry from P2. While I am adding this this P1, while I am computing this P1, at that time the sum bit is basically the P1, but the carry which is produced because of this particular addition operation, so that will come over here. Okay. So, that is why here you see that sum bit, that is P1, but the carry bit is basically coming to the next, and in this case this is considering this A2 x0. So, A2 x0 and A1 x1. So, this will produce this carry over here and sum will come to this. Okay. So, if this is P5, so sum will come to this, then again that will be added with A1 x2 and the C1 from the previous case. So, C1 is coming over here, so and A0, sorry, this will be A0 x2. So, A0 x2 is coming over here. So, finally, it is producing this P2 and the corresponding carry C2 is going to the next level for calculating this P3. So, then again the P3 will be considered this, and again that will be C2 will come down to this particular position. Then again in each stage the corresponding carry is forwarded to the next level. Okay. So, then what is the, that means corresponding critical path in this case? Which one will be the maximum, that means the path which is considering from the input to the output. Okay. So, where I will get the maximum of that means where I will get the maximum critical or the maximum depth I will get if I consider this corresponding that operation of this unsigned multiplication or multiplier architecture. So, at that time the middle position, which is nothing but this, I think P5, no, P0, P1, P2, yeah, P5. So, for P5 position I will get the depth as maximum one. Okay. So, P5 or P4, I think P5 or P4. Okay. So, at that time if I consider, that means for P5 or sorry for P4, this is the path it is following. Okay. So, and for P5 this is the path it is following. That means, for P4 and P5 both are basically consuming 4 processing elements in this particular direction. Okay. So, then if I consider that each of the processing element is nothing but one full adder cell considering this 3 input bit and it produce this 2 output bit. Okay. So, then if I consider this, so that means this particular architecture, so this will be the corresponding this P4, and not only this P4, again as this P4 is basically again coming to this, that means this is coming over here, then at this particular position is also it is traversing to produce this P6, P7, P8 and P9. Okay. So, that means the total path which is basically the total critical path over here, which is nothing but then this to this. This is the maximum path which I am getting for computation of P9. Okay. So, now that means if we consider this array multiplier architecture, the structure is very much regular, but the delay is more, because the carry is rippling through the corresponding array. Okay. So, that is why this array multiplier architecture, this will gives you one better, that means implementation, on the implementation aspects it will be better, but for the other constraint it will be not that much advantageous. Okay. So, then we have seen this that Boguli multiplier, 2's complement Boguli multiplier is something like this. So, this is the equations which we have got in Boguli 2's complement multiplier. So, now my question is that, is this particular this operation or this table, can it be represented using this array multiplier architecture? If it can be, so at that time how it can be represented or implemented via this array architecture, that we will see in the next class. So, this is it. Thank you for today.